So welcome everybody to this joint IFAC IEEE, the Control System Society webinar series on nonlinear control system, which is an initiative from both the technical committees on nonlinear control of IEEE and IFAC. Today we welcome Professor Arjan van der Schaft, which is well known in the field and has given great contributions, as already all of us know, to the nonlinear systems theory. So Professor Arjan van der Schaft will talk about Port-Hamiltonian system theory and monotonicity. A brief recall of his bio sketch. So he received the undergraduate and PhD degrees in mathematics from the University of Groningen. Then he moved to the University of Twente and came back to Groningen, where in 2005. He is fellow of the IEEE, fellow of IFAC. He has been awarded a Certificate of Excellent Achievements from the IFAC Technical Committee of Nonlinear Systems, and he was invited speaker in many conferences and international meetings. Between this, the International Congress of Mathematicians in Madrid, and he has co-authored many books that all we know. From between this, the nonlinear dynamical control system with Niemeyer, to gain and passivity techniques in nonlinear control, and many others. So thank you very much for being here and for giving this very interesting talk. Thank you. So
okay.
I'll stop sharing.
Yeah.
Okay.
Okay, thank you very much for your introduction, and thank you for the invitation to give this talk. Let me, right. Okay, yes, so this is joint work with my colleague Kanat Chanlibel. And the aim is to discuss the connections between, on the one hand, Port-Hamiltonian systems, which are basically stemming from physical system modeling, and on the other hand, monotone relations, which are stemming from convex analysis and optimization and other areas. So the basic idea of a Port-Hamiltonian system can be explained by this cartoon. So the idea is that we model our physical system by ideal components, which are basically divided into three groups. So there are the pure energy storing elements. So that is corresponding to this blue balloon. And there is the corresponding Hamiltonian, or total energy. And then there is, in this brownish orange balloon, there are the dissipating elements, so like dampers or resistors in the electrical domain. They can be linear, nonlinear, they can be continuous, they can be discontinuous. And then thirdly, there is this yellow balloon, which is the Dirac structure, as we call it. And that is containing the basic interconnection laws, like Kirchhoff's laws, as well as elements like transformers and gyrators that do not consume or store energy. So they are only power routing And so the variables E and F and U and Y in this cartoon, they are conjugate vectors whose, and they are living in dual spaces, and the product of them is equal to power. So ES times Fs is equal to the power that is going into the energy storing elements, for example. And this Dirac structure that is such that the all the efforts and flows, so all the E and F and the inputs and the outputs, they are related in such a way that the total power is equal to 0. So the Dirac structure is power conserved, like a Kirchhoff's laws. Okay, so the formal definition of a constant Dirac structure in this case. So there is also a more general one on the manifolds, but I will only talk about constant Dirac structures. So a pure linear algebraic definition is a subspace of linear space F times its dual E, such that the total, that the product of the vector E and F is 0 for all the pairs in F, E, and D, and such that the dimension of D is maximal, and that turns out to be equal to the dimension of F, or the dimension of E. That is the same. And then a simple example of a Dirac structure is the graph of any skew symmetric map J, say from E to F or from F to E. And dissipation is also very easy. So dissipation means that we have laws that are such that the product of ER and FR, so the efforts and the flows that are entering into the energy dissipating elements, that this is always characteristical than 0. And all this implies that any Port-Hamiltonian system is passive or cyclopassive, and that the Hamiltonian function is a storage function. Okay, and this is a very simple example for those of you who have not seen this before. So take the simple example of a DC motor. So how do we model this in a Port-Hamiltonian fashion? Well, we have 5 ideal elements. So we have 2 energy storing elements, one corresponding to the storage of magnetic energy in the inductor, and one corresponding to the storage of rotational kinetic energy. And there are 2 energy dissipating elements, so one in the electrical domain and one in the mechanical domain. And there is a gyrator K, which is converting mechanical power into electrical power, and conversely, in a power conserving manner. And then we have 2 ports. There is the electrical port with input and output variable V and I at the left-hand side. And then there is a mechanical port with the inputs and the outputs being given by the torque and the angular velocity of this rotating inertia. And then we just write down the equations for all the elements. And here I take the simple case that all the elements that are linear, but you can also do this for the nonlinear case. So we have the inductor and the inertia. So these are basically integrators corresponding to an energy storage. And in fact, if we sum the two terms, then we get the total Hamiltonian. And then we have the energy dissipation, which is being specified like this in the linear case. And then we have the gyrator, which is corresponding to a positive constant K, and which is converting, as I said before, mechanical into electrical power, and conversely, depending if we use it in a motor or in the dynamo mode. And then the Dirac structure is, in this case, is determined by the interconnection equations, which are given like this in the electrical domain and this in the mechanical domain, plus this gyrator, and then we eventually get this structured dynamical input state output system, where we identify here this skew-symmetric matrix corresponding to the gyrator, and here we have energy dissipation, and this term corresponds to the gradient of the Hamiltonian, and that also appears in the output equation as well. Okay, so that's very briefly about Port-Hamiltonian systems, so which is, as I said before, which is really corresponding to passivity, but much more than that. Also, all kinds of conserved quantities can be studied within this framework and other properties. And then, secondly, we look at monotone relations, where we again start from a linear space F and its dual, denoted by E. And then we call any subset M of F times E, we call it monotone if for all two pairs F1, E1 and F2, E2 in M, that we have that this inequality holds. There is a strengthened property, which is called cyclical monotone, if in fact for all M, this inequality holds. Yeah, for all Fi, Ei in the subset M of F times E. So by just taking M to be equal to 1, you see in fact that this inequality, that it reduces to the former inequality. Now, a simple example of a monotone relation, and in fact also cyclically monotone in this case, is this continuous relay characteristic. So -1 for x less than 0 and +1 for x greater or equal than 0. Now, this example already suggests a strengthened definition, and that is what is called maximal being maximal. So we call a relation, we call it maximal monotone or maximal cyclically monotone. If it is monotone or cyclically monotone, and we cannot extend it while keeping this property of monotonicity or cyclical monotonicity. So there is no larger M prime, which is cyclically monotone, covering the whole N. So only this. So this previous example was not maximal, because in fact we can close it by defining for x is equal to 0, we can define y to be in the whole interval between -1 and +1. Yeah, so we get a multi-valued map which is, of course, the typical description of the ideal Coulomb friction. And this one, you can check, this is maximal, so we cannot extend it any further. By the way, there is a very nice paper by Carsten Scherer in one of the Control Systems magazine special issues, where there's also a very nice story about cyclical monotonicity and dissipativity. Okay, and very important, why are these cyclical monotone relations so important? Well, they precisely correspond to convex functions. So that is where an important link to convex analysis appears. So any maximal cyclically monotone relation is being given as the graph of the subdifferential, which we denote like this, of a convex function, which can also take values plus infinity. So we call that an extended function. So subdifferential, because, well, this is just the ordinary differential in case k is differentiable, but also for general convex extended functions, we can still define something like a generalized notion of derivation, which is then called the subdifferential. So I will not go into any details about this, but just give the main flavor using this example of a Coulomb friction. Because what is the convex function which corresponds to this Coulomb friction characteristic? Well, that is just the modulus function. Yeah, so the function modulus of x, with x in R. And indeed, this is differentiable, of course, for x less than 0, corresponding to a value of -1, and it is clearly differentiable for x positive, corresponding to +1. And then at 0, it is not differentiable, but what we do is that we take the envelope of all the possible tangent factors to it, which is just the interval from -1 to +1. So indeed, we are back to the Coulomb friction characteristic. So you see that convex analysis, of course, gives a very nice approach to dealing with discontinuous phenomena, at least if they are convex. And then one more notion that I will need later on, that is the well-known notion of conjugate function, which you know very well from convex optimization. So if you have an extended convex function k, like before, then on the dual space E, you can define this conjugate function, defined like this, and then you can show that this is also convex. And if k is lower semi-continuous, then taking twice the conjugate, that brings you back to the original function. And furthermore, E is in the subdifferential of k corresponding to a certain f, even only if f is in the subdifferential of k star, the conjugate for this E. All right, so that is the basic ingredient now to come to a combination of, on the one hand, Port-Hamiltonian systems, and on the other hand, maximal monotone relations. Because what we do is that in this cartoon of the Port-Hamiltonian system that we replace the combination of the Dirac structure, so this yellow balloon, and energy dissipation, so this brownish orange balloon. We take the combination of these two and we replace it by a maximal cyclically monotone relation. Yeah, so we look at an N, which is now a subset of, well, F times E. F and E, they are the variables in the cartoon corresponding to, which are linking to energy storage, to the Hamiltonian. And Y and U, they are the spaces where the of the outputs and the inputs. And then the dynamics of the what we call of the semi-Port-Hamiltonian system, which defined by this M, is now being given like this. So we require that for all t, and that the pair of minus x dot, which is in this space F, and the output, which is in this space, and then the gradient vector of the Hamiltonian, which is in the dual space E, and the input, which is in this space capital U, that they are in this maximal cyclically monotone relation M for all t. Yeah, and so we have different possibilities, and depending on if this is cyclically or not, or if it is maximal or not, and this kind of umbrella terminology we will sometimes use incrementally Port-Hamiltonian. So let's first focus on the cyclical case. So that means that such Port-Hamiltonian systems, that they can be represented into this form for a certain function k. And so I was mentioning that if this is cyclically monotone, then there is a convex extended function, which is depending on E and on U, such that the subdifferential of this function is equal to this cyclically monotone relation M. Yeah, so we get a function description like this, where in general we have here inclusion. So this is corresponding to what you can call a multi-valued map. So here we take the partial subdifferential with respect to the first component, E, and here we take the partial differential with respect to the second component, U. And of course, if k is an ordinary differentiable function, then we have this nonlinear system class, which is being specified basically by two functions. So this convex function k, together with a Hamiltonian h. Okay, let's go quickly to examples in order to make that more clear. So one is the case of a network of a nonlinear RC circuit. So we consider an electrical circuit with conductors, so the inverse of resistors at the edges, and we have at the nodes, at part of the nodes, we have grounded capacitors, and then the rest of the nodes, they are terminals corresponding to input voltage potentials. So we decompose the incidence matrix of the circuit graph D corresponding to the capacitor nodes and the terminal nodes like this. Now the conductors sitting at the edges, they are given by general nonlinear expressions. Say, we can express the currents as functions of the voltages. And we assume that all these functions that they are monotone, and for simplicity, we will take them to be continuous, although in fact, we can also do it in the discontinuous case. Now, if it is continuous, that means that there is a convex and differentiable function corresponding to every edge, such that we have in fact this. So, like this. Now, then we define the full function k hat depending on the voltages at or the across the edges like this as the sum of all these functions. And then we have that the vector of currents through the edges is being given like this. Now, by Kirchhoff's current laws, we know that the incidence matrix times the vector of the currents is equal to this vector, where these are the incoming currents at the capacitor nodes, and these are the incoming currents at the terminal nodes. Furthermore, we know that the voltages across the edges, that they are being given like this, where psi is the vector of the voltage nodal potentials, corresponding, and here split correspondingly to the capacitor and the terminal nodes. And then finally, we get our function k, which is just being defined like this. So we basically take the function k hat, and then we substitute for v this expression. And it is then easy to see that gradient vector of k is being given like this. And well, these are the currents, so this is equal to this, so this is equal to this. And then we also know, then we add the equations for the capacitors, which is just this, and that the voltage potentials are being given as the gradient of the Hamiltonian, which is in this case the total electric energy. So we indeed do get the system class as we saw before for this function k, where the inputs are the voltage potentials at the terminal nodes, and the outputs are the currents at the terminal nodes. And the same equations, for instance, you also get for nonlinear mass damper systems, with the difference that always this Hamiltonian, which is then the kinetic energy, is a quadratic function. Another example, but now coming from convex optimization, is a standard gradient algorithm for computing the minimum of a convex function, say from Rn to R. And normally we do that in discrete time, but we can also do it in continuous time. And then we get a set of differential equations like this, where tau is in the positive definite matrix, determining the time scales of the algorithm. This is a simple example of a maximal cyclically monotone Port-Hamiltonian system. Well, it's if we define X to be tau, the matrix tau times the vector Q, then we can also write it like this. And then Q is being given as the gradient of the Hamiltonian being given by this expression. Yeah, and the monotone relation is, of course, the graph of this convex function that we want to minimize. We can also include inputs and outputs. For instance, if you want to do distributed minimization, so if you have several interconnected minimization problems, so then you could add to P, you could add terms like this, and then you can consider cyclically monotone Port-Hamiltonian systems like this. And you could also take the case that you do not have a fit-through over here, and then you can also consider this. But by the way, this is not cyclically monotone, but this is just ordinary maximal monotone. Another example from convex optimization is a primal dual gradient algorithm in continuous time, where you want to minimize again convex function P, but now subject to affine constraints. So constraints AQ is equal to B for some matrix A and a vector B. So then you, of course, you consider the Lagrangian being given like this, where these are Lagrange multipliers, convex in Q and concave in lambda, and then the primal dual gradient algorithm in continuous time is being given like this, and where again you have some matrices over here for specifying the timescales. And this can be again formulated as a maximal monotone, but not cyclically monotone Port-Hamiltonian system. And it takes this form where now the Hamiltonian is, is corresponding to xq, where, okay, again, I take xq to be the product of tau q times q and x lambda, this product. And now the Hamiltonian is involving this xq, but also x lambda, which is a dual vector to the Lagrange multipliers instead. I'm sorry. All right, so these are, so you see that examples that they stem from physical system modeling as well as from convex optimization. Now, a very important key element of this theory, which is very similar to the theory of standard Port-Hamiltonian systems, is that we can interconnect also these Port-Hamiltonian systems corresponding to maximal monotone relations, and that we still get another maximal monotone Port-Hamiltonian system. And that is based on the observation that if we take two monotone relations with partially shared variables, that their composition is again maximal monotone. So how do we define this? Well, let's take an MA involving FA and F and EA and E. And this F and E, that is also present over here. And here we have FB and EB. And we are going to compose these two monotone relations via the variables F in capital F and E in E. So we define the composition as all the FA, FB, EA, EB, for which there exists an FE in here, such that this is in MA and this is in MB. Yeah, so in other words, when we look at these vectors, we set F1 to be minus F2 and E1 equal to be E2. Well, it is quite easy to see that if MA and MB, if they are cyclically monotone, then so is the composition. What is much harder to show is that that also holds for maximality. And in fact, we need to impose some very weak technical conditions for this to hold in general. And I will not dwell upon these technical conditions. They are detailed in the paper that I will mention at the end. What is also nice that in the case of cyclically monotone relations, that the convex function corresponding to this composition can be computed based on the convex functions corresponding to MA and to MB. And the construction is sketched over here. So if we have this Ka and this Kb, then what we do is that we define this KAB, like this. And then we take the convex conjugate of this thing, and we put E to be equal to 0. And then we take the conjugate of it again. And then what we get is eventually is this function. By the way, this is kind of a nonlinear analog of taking Schur complements. Or at least I think that this is a useful analogy. Well, some consequences of this basic interconnection theorem is that power-conserving interconnection of these incrementally Port-Hamiltonian systems, that they are again Port-Hamiltonian, incrementally Port-Hamiltonian. Well, if we come back to ordinary Port-Hamiltonian systems, so you can easily show that constant Dirac structures, that they are also maximally monotone. And thus the composition of a constant Dirac structure, as we did in the cartoon, with energy dissipation, but now assume that this is maximally monotone, that is then also going to be maximally monotone. So in this case, we see that an ordinary Port-Hamiltonian system is also a maximally monotone Port-Hamiltonian system. By the way, Dirac structures are typically not cyclically monotone. In fact, it turns out that they are only that if and only if they are of Kirchhoff type. So if we can split the linear equations, like equations involving only the currents, and dual equations involving only the voltages. Okay, there is also a corresponding linear theory, which is of course much more easy. In that case, you can show that any maximal monotone subspace can be always written as the composition of a Dirac structure and a linear energy dissipation. So in that sense, the two notions of Port-Hamiltonian systems, they coincide in that case. Okay, well, I will go quickly through this. So you can use this for steady state analysis. So if you consider an arbitrary system like this, then the steady state input-output relation are all the y bar u bars for which there is a steady state x dot, so satisfying this. Well, if we have here an incrementally Port-Hamiltonian system, then you see that this steady state input-output relation is in fact also, well, at least monotone, and under certain conditions, it's also maximally monotone, and you can also extend that to cyclically monotone. Well, we'll take more time for discussing now, finally, the dynamical properties of these incrementally Port-Hamiltonian systems. Well, the basic dynamical property of any monotone Port-Hamiltonian system is this incremental property over here. So for any two solutions, x1, x2, to the incremental Port-Hamiltonian system corresponding to two input functions u1 and u2 and corresponding output functions y1, y2. So we have this inequality. Now, what you see is if you additionally assume that the Hamiltonian, if this is strictly convex, then if we define this, what is called in convex analysis, the Bregman divergence, but in fact, this is also called a shifted Hamiltonian, and it goes back to many old papers in thermodynamics and also in nonlinear control. like a paper by Yaya Wardana and Romeo Ortega. So if we define this shifted Hamiltonian, then this is again strictly convex for any x bar. And furthermore, the gradient of this function is just being given like this. So if we now take x2 to be a steady state, so corresponding to x2 bar equal to 0, and u2 and y2 to be the steady state values, then we get this inequality, which is really the shifted passivity property. And this holds for any steady state x bar. So this is what is called equilibrium independent passivity. So for any steady state, we get passivity. So incrementally Port-Hamiltonian systems, they are equilibrium independent passive. Well, Port-Hamiltonian systems, they are passive, or at least cyclopassive. So one would wonder if they would be then also incrementally passive. Now, that's a more delicate story. So let's again consider this incremental property. Well, if the Hamiltonian, if it is quadratic affine, so an expression like this, then you see indeed that this inequality, that it reduces to this. So we get a storage function for this incremental supply rate. So indeed, this is incrementally passive, assuming that the Hamiltonian is of this form. And the same also holds for the differential passivity. Well, in the examples that we have seen, like the mass damper system and the gradient system and the primal dual gradient algorithm, indeed, every time the Hamiltonian was quadratic. On the other hand, for the RC circuit case, if we consider nonlinear capacitors, that is not the case. So then we do not immediately get this incremental passivity. And in fact, as was noted by quite a few people before, there is an intrinsic problem over here. Because if we just have the simplest case, if we have a single nonlinear capacitor, so x dot is equal to u, y is equal to the differential of some function h, well, this is obviously maximal monotone Port-Hamiltonian. Well, when is this incrementally passive? Well, then we need that there is a storage function S, depending on x1 and x2, satisfying this. But that inequality is equivalent to this one. And then if we differentiate the first equality, with respect to x2, so then this drops out. Then we get this, and if we differentiate the second inequality with respect to x1, then we get that it is equal to this. I'm sorry. So we see that this means that the Hessian of H should be constant. So, but that of course just means that H is a quadratic affine function. So we come to the conclusion, as was noted by quite a few people before, that a nonlinear capacitor is only incrementally passive if it is a linear one, which is a bit disappointing. So that's a major open question. What are the dynamical properties? Well, one more thing that I would like to point out is that these cyclically monotone Port-Hamiltonian systems, they also suggest an alternative stability analysis approach. So let's consider the simplest case where we do not have inputs. We just have an autonomous system being given by a function k of E and an Hamiltonian H. Well, then of course the first Lyapunov function candidate is just the Hamiltonian and the energy. And indeed, if this is less than or equal to 0, as we have in ordinary energy dissipation, then, well, we have the inequality. But the problem sometimes is that the minima of H, that they do not correspond to the equilibrium that you would like to investigate. On the other hand, we can also rewrite the dynamics in terms of the conjugate factor, like this, where here is the Hessian of the Hamiltonian appearing. And then the function k, so corresponding to energy dissipation, is popping up as a candidate Lyapunov function, because ddt of k is also less than or equal than 0, at least if the Hessian of H, if this is positive. So I think this is something that has been used in various contexts. In fact, it's also going back to the classical Breto-Moser equations for nonlinear RC circuits. So this is an approach which deserves more attention. All right, then I come to the conclusions of this talk. So I think that these incrementally Port-Hamiltonian systems, that there are several convincing examples, both from engineering, from physical system modeling, and from convex optimization. And what is very nice about it is that there is there's a close connection to convex analysis and the whole powerful theory of this. And that one of the advantages is that this can deal with all kinds of discontinuous and multi-valued nonlinearities. So, of course, the classical geometric nonlinear control is basically concerned with differentiable, with smooth dynamical systems. And putting it into this convex analysis framework allows you to also to deal with all kinds of discontinuous phenomena in a powerful way. From a geometric point of view, I should also add that, of course, convexity is not a purely coordinate-free notion. Huh? So if you have a convex function, and if you apply arbitrary nonlinear transformation, then convexity need not be preserved. So there is a need for geometry, where you start with a given set of coordinates, and then you will only consider linear affine changes of coordinates. Now, something that I did not talk about is that this framework can be also used for computing equilibria of networks of incrementally Port-Hamiltonian systems. As I was mentioning already, the dynamical properties of incrementally Port-Hamiltonian systems, they are still somewhat elusive, so they do not necessarily correspond to incremental passivity. They are a bit different. There is one possible generalization that we studied in the context of DAE systems. There is another one is that we replace the Hamiltonian H, or in fact the gradient of this Hamiltonian H, by general Lagrangian submanifolds. This is a very powerful idea in the context of DAE systems. By the way, in many cases, these Port-Hamiltonian systems, they are mixtures of differential and algebraic equations, so DA systems. Okay, and the basic reference for this talk is the paper quoted here, which is going to appear in the SciM journal, Control and Optimization. Thank you very much for your attention.
Thank you very much. So let's see if we have any question from the audience. Not in chat.
Can I ask a question?
Yes.
Yeah. Okay.
Thank you.
Thank you very much, Arjan, for this nice presentation. As you mentioned, dynamical properties is a bit. I was wondering that there is a notion of monotone systems also based on the partial order of trajectories, right? So do you see there is a connection between incrementally Port-Hamiltonian systems? Because here you consider the monotone relation between effort and flow, which is not really based on trajectories.
No. So indeed, so there are different meanings of the word monotonicity. Mm-hmm. One is the one, so I was talking about monotonicity in the convex analysis context, so monotone multivalued maps, monotone relations. So there is also the notion of, which you were referring to, of monotone dynamical systems, which is basically that you have invariance of cones. Yeah, so that if you start somewhere, then all the coordinates will increase. And that's a different notion. Well, there are some connections, but that's not so clear to me. Let's put it like that.
Okay. Thanks for the answer.
Any other question? So there are people thanking you for the talk. I think we have a question from Christophe.
Yes. Thanks, Julia. Thanks a lot, Arjan, for the very interesting presentation. So I learned always when I'm following your lecture, I always enjoy a lot, and I'm always learning a lot. So thanks a lot for your great job and your very interesting lecture. So I was wondering about, so you have discussed this with gradient, descent gradient, you know, at around slide 20 or 21, something like that. So I was wondering if we can use this approach for discrete time. It is just a curiosity and maybe too naive question, but can we make your study for discrete time systems, and can you use this algorithm for in optimization to make an optimization algorithm by writing again the gradient descent ID, but in discrete time and for numerics?
Okay, that's an interesting question, and I should confess that I have not thought about that. Well, of course, so the whole definition that I gave about these incremental Port-Hamiltonian systems, that is in continuous time.
Yes.
Okay.
More generally, maybe one other way to say that is, so you have dealt with monotonicity and with stability at the end of your talk, but what about the performance? So can you ensure some performance or something like that? No?
Performance of
the stability or when you are designing the K controller?
Well, you know,
yeah.
Okay. So,
yeah, exactly.
So I mean, one. Okay, so the simplest case, let's talk about that, is if you have if of the equation over here is if you have a mass with momentum x, and then k is corresponding to the Rayleigh dissipation function for the damper. So you have a nonlinear damper, and then so x is the momentum, and then the Hamiltonian is, in that case, is just the kinetic energy. So the gradient of the Hamiltonian is just the velocity of the mass. So you have an term over here which is depending on the velocity of the mass, and what you are trying to do here is to use this Rayleigh dissipation function as an Lyapunov function, yes. Right? So that can have some that, as I mentioned, so the Hamiltonian is, of course, is the typical candidate for a Lyapunov function. But if you want to investigate the stability of an equilibrium which is not the minimum of the Hamiltonian, then you could also try to do this. And in fact, that is what was also classically done in the Breaker-Moser theory for RC circuits. Well, there it is in fact more complicated because there are LC circuits are being considered, but let's just look at the RC case. So there you have very simple linear capacitors are being considered, but then the problem is in the nonlinear resistor, and you want to determine the stability, and which is being complicated by this nonlinear resistor. And then, in fact, in the Breaker-Moser theory, to the Rayleigh dissipation function corresponding to the nonlinear. So, I mean, I was just adding this as a slide to my talk. So I did not do any systematic work about this, but I think it is something to be pursued.
Okay, thanks. Maybe for your next lecture. I'm looking forward to follow it. Thanks again, Arjan.
Any other question? So I had a question connected with Christoph. So I was wondering which were the difficulties in moving to discretized or discrete time systems?
Yeah, well, again, I haven't thought about this. And then that is probably because I'm too much biased towards physical system modeling, where this is primarily in continuous time. Well, I mean, even for ordinary Port-Hamiltonian systems, giving the discrete time analog of it is not so obvious. But it's interesting because maybe in this case, using these maximal monotone relations, discrete time is more easy. But again, I cannot say anything reasonable about this.
Thank you. So there is one question more from Bayu.
Yes, thank you, Arjan, for the lectures, and it's very clear. And of course, you may know my questions or my interest, and that is on the equilibrium independent passivity. So you mentioned that indeed in the RC, then in the RC circuit, then it has to be a linear capacitor. But if we are dealing with the RLC, then we can deal with a nonlinear capacitor. Am I correct? For the
okay, well, okay. So the these incrementally Port-Hamiltonian systems, if you additionally assume that H is convex, which is a reasonable assumption, then they are equilibrium independent passive.
Yeah.
Now, here the story here is about incremental passivity,
Yeah, all right.
and this is more difficult.
Yeah, yeah.
So if the Hamiltonian, if it is not only convex, but if it is quadratic affine, then you get incremental passivity. Yeah, but in general, the story for incremental passivity is a bit confusing. And I think this was also being discussed by in the previous lecture by Rodolphe.
Okay, yeah.
Because well, say a nonlinear capacitor, so in the very, very simple case, that is a maximal monotone Port-Hamiltonian system, but it is, in general, it is not incrementally passive. In fact, it is only incrementally passive if the capacitor is just a linear capacitor, so that we have a linear equation over here.
Yeah, yeah, clear. Okay, thanks, Arjan.
So I check if we have questions on. So is there any other question? If not, okay, so thank you very much again for this great talk and really illuminating. Thank you very much.
Okay, thank you.
See you next time then.
Bye-bye.
Bye.